In this video, we will explore one of the key properties of polygonal masonry. And since it occupies a central role, it is reasonable to assume that it forms part of the function and meaning behind polygonal structures. This property is single lithology. It gives the constructions a uniform, one could even say monotonous appearance. At the same time, it helps the complexes blend harmoniously with their surroundings. And for this very reason, single lithology often goes unnoticed. In modern construction, materials are selected based on how well they meet the requirements of specific structural elements, such as foundations, the main load-bearing component that distributes the weight of buildings and structures; walls, including load-bearing ones; floors and lintels, and so on. These elements are typically made of concrete, including reinforced concrete, steel, timber, various types of masonry, natural stone, bricks, aerated concrete, ceramic blocks, and mortar. On this basis, the building is constructed as an integrated whole. In ancient times, this variety of materials did not exist. Still, in ancient Rome, different materials were used even in the foundation parts of structures, and the construction process itself involved a rather complex sequence of action. Vitruvius described the use of different materials. Or a quote from Auguste Choisy, describing Roman wall construction: "In Inca domestic architecture, various materials were also used: stone, clay-based mortars, timber, and reed." Polygonal masonry structures, however, are nothing like that. They are built, from bottom to top, entirely out of blocks made from a single rock type. This implies two distinct principles. First, the exclusive use of stone, and second, even more significantly, the use of a specific rock type not just within one building, but across the entire polygonal complex. The first principle allows for relatively straightforward explanations: why stone alone might have been chosen for constructing a polygonal complex, and why this approach would have been acceptable. Polygonal wall niches are typically single-storied and roofless. They were not originally intended to have roofs, as was discussed in detail in the video series focused on buildings. Thus, there was no need for wooden beams or roofing structures. Lintels over openings could easily be made from the same type of stone. Apart from the wall niches, other elements of the complex, stone facings, hydraulic systems, stone layouts, and configured grottos, clearly required no additional materials beyond stone. There was simply no need for anything else. However, this does not automatically mean that only one specific rock type had to be used. And yet, that is exactly what the second principle implies. This, too, might seem explainable in simple terms. For example, the most accessible material was used, the one found closest to the construction site. As a result, all structures within a complex would have been built from a single local rock type. However, natural rock falls are rarely composed of just one lithology. This is clearly visible on the slopes, where a wide variety of stone types can be found. So when mortar-based construction is employed, one can often see stones of various kinds being used, as long as they are strong enough and of a shape suitable for masonry. Therefore, if all available stones had been used indiscriminately, the resulting masonry would naturally be composed of mixed lithologies, except in rare cases where only a single rock type is present in the vicinity, such as around Machu Picchu. But such situations are exceptions, not the norm. One could also suggest that the use of a single type of stone was a practical decision. Perhaps it was simply easier for the builders to work with a uniform material when shaping and fitting the blocks, as it would have the same hardness, fracture behavior, and general characteristics. But if that were the case, we would expect to see a preference for local stone types, and especially for those that are softer and easier to work. In reality, though, the choice of block material often followed a different logic. The polygonal masonry along Inca Roca Street in Cusco is made of diorite. Despite the presence of large limestone formations in the immediate surroundings of the city, diorite was used deliberately, even though the nearby limestone would have been easier to work with. A similar question arises in relation to the Coricancha complex, which was built from andesite. Of course, one could argue that andesite and diorite were preferred for their durability and weather resistance, as well as for aesthetic considerations, including color. But that argument has weaknesses. Dense limestone, as centuries have shown, is also quite resistant to erosion, and its color does not differ significantly from the gray of andesite. Moreover, we see no use of the classic architectural technique of combining different stone types for different building elements, for instance, to highlight doorways or portions of walls. And this is particularly important, since traditional historical interpretations often assign such a decorative or accentuating function to polygonal masonry, claiming it was used to emphasize certain important buildings or their parts. If that were true, we would routinely see facades where only the front or the area around an opening is built in polygonal style, while the rest is constructed more crudely or with different methods. But such selectivity is only found in modern restorations, where surviving sections of polygonal masonry have been supplemented with readily available materials. The general rule is that the entire structure is built in a consistent style, with the same level of craftsmanship throughout, without any special emphasis on individual zones. The same applies to the Temple of the Sun at Ollantaytambo. Its megalithic blocks were made from pink rhyolite transported from a quarry located across the Urubamba River Valley. And yet, when building the Temple of the Ten Niches, pre-shaped blocks, abundantly available nearby, were not used. Instead, only blocks of local gray andesite were employed. The only exception is a reused rhyolite block in the base of one opening, right where the masonry breaks. As we can see, material was not chosen based on proximity to the construction site. It is well known that some quarries were located dozens of kilometers away. The stone for these complexes was selected deliberately, and difficulties in transporting it were not seen as an obstacle. A remarkable example of disregard for ready-made blocks of a different stone type can be found at Sacsayhuaman. In the rubble fill behind the zigzag walls, exposed after partial collapse, excellent andesite blocks were discovered. This seems almost absurd. High-quality blocks were simply discarded, treated as nothing more than rough stone, as construction waste. Yet when we take into account the requirement of single lithology, this approach becomes understandable. The andesite blocks had no place in the limestone masonry of the crenellations. It's important to remember that those andesite blocks had earlier been transported from relatively distant quarries. This means that, at the time when the andesite structures were being built, this particular stone was intentionally chosen. Limestone was deliberately avoided. Then at some point, something changed. By the time the limestone walls were being constructed, the previously valuable andesite blocks were left unused. But why insist on using only one specific type of stone for the entire structure? It should be noted that single lithology ensures consistent physical properties. From the velocity of acoustic wave propagation, which is known to be highly sensitive to the medium's composition, to thermal expansion. Accordingly, single lithology provides a degree of stability and predictability in the behavior of structural elements and of the entire structure itself. From this perspective, we find a highly plausible explanation for the otherwise curious preference for dry masonry, that is, construction without mortar. The use of mortar introduces multiple boundaries between different materials, and these boundaries complicate the way physical processes unfold. By avoiding the labor-intensive process of precise block fitting, builders could save time. But they would sacrifice the ability to predict the structure's behavior as a unified object. This is precisely why masonry that may resemble megalithic construction, but lacks tight joints, was never used in polygonal complexes, just as mortared masonry was not used. They are fundamentally unsuitable, even if, as mentioned in the video series on construction principles, they can be just as durable. And indeed, partially fitted masonry has stood the test of centuries without major degradation. If material homogeneity is a foundational requirement, then it would be logical to maximize the use of bedrock. And that is exactly what we observe in polygonal construction, where masonry often complements and extends natural rock formations, adding the necessary volume and shape. This is most clearly seen when masonry and bedrock form a unified entity, with the masonry filling natural voids in the rock. A striking example of this approach is found in the lower tier of the Temple of the Sun at Machu Picchu, where masonry is used to close gaps and create niches. However, the use of natural bedrock also has its drawbacks. Rocks are naturally fractured, sometimes densely, and often contain flaws and inclusions of other materials, which can affect a wide range of physical characteristics. Therefore, a structure built using polygonal masonry could actually surpass in quality a similar structure carved entirely out of solid rock. In other words, the goal was to create an artificial equivalent with targeted properties. Moreover, constructing a structure from a single, massive outcrop of bedrock, in the full volume and required shape, is, in most cases, simply impossible. Such natural resources are often unavailable in sufficient quantities, and in some places, there may not be any usable rock formations at all. However, using polygonal masonry to shape stone forms has its own drawbacks. Joining blocks along curved surfaces, even with the inclusion of interlocking features, cannot fully replicate the function of mortar. To ensure structural stability, an additional set of techniques was required, described in detail in the video series on construction rules. Briefly, these include inclined wall faces, use of backfill as lateral support and stabilization, specific types of masonry patterns, reinforcement of corners with megaliths, and maximum utilization of solid bedrock foundations. All of these methods demanded considerable effort and highly specific skills, which may indicate that the use of polycurved masonry was in fact a necessary compromise, a solution born from the limitations in the availability or scale of natural stone formations. At the same time, it was also a method to augment and enhance the required properties of the structure. In other words, this was a technology whose primary goal was to alter and improve the characteristics of natural rock, ultimately creating an artificial, optimized analog. This raises an important question: how were the blocks inspected for internal cracks? This is a key issue even in modern stone quarrying, where techniques like ultrasonic flaw detection are used. Interestingly, cracks in polygonal blocks are rare, and when present, they more often appear to result from seismic activity over time, rather than from original flaws in the stone. By contrast, natural rock surfaces are typically covered in a dense network of fractures. Selecting usable blocks from them would require exceptional care, particularly in the case of megaliths like those at Machu Picchu or Ollantaytambo, which show no visible fractures. That the stone was chosen deliberately and carefully is further supported by the fact that many limestone blocks produce a melodious ringing sound when struck, an indication of homogeneity and good acoustic conductivity. It's clear that such acoustic properties could apply to individual elements or even to entire structures as unified resonant bodies. All of these complexities, the need to select suitable material, to transport it, and to fit it precisely, point to one thing. Polygonal masonry, or more specifically, precision-fitted dry masonry, was not the result of perfected technique or convenience, but rather of necessity, a forced solution to the inability to use solid bedrock, which in reality is fractured, heterogeneous, or insufficient in size. No other known method could achieve a comparable outcome. And perhaps this very difficulty, this impossibility of simplification, is the reason for the numerous unfinished segments of walls, and even entire structures, that we still find today. And in this case, it makes sense to ask, were the goals set by the creators of the polygonal complexes actually achieved? Did they succeed in translating their intentions into something functional, using only the available natural elements? We will explore possible answers in future episodes. But for now, let's turn to the fact that, despite the ability of masonry to replicate natural rock formations, many complexes contain features that apparently could not be replaced by block-built constructions. Intihuatanas, for instance, are always carved from solid rock formations. Conversely, buildings or rows of identical trapezoidal niches are never found carved directly into bedrock. There are no known examples where even a single wall niches is cut fully from the rock, even though it would have been much faster to carve a row of niches directly than to fit multiple blocks together. When we construct buildings, whether as dwellings or as enclosures for equipment, the individual physical properties of materials are not our primary concern. What matters is whether the structure fulfills its function. But these physical characteristics become critical when the structure itself is functional. As in the case of a bridge, where everything matters, the materials used, the construction methods, and the natural frequencies of the structure and its parts. And this is exactly what we observe in the polygonal complexes. Moreover, it becomes clear that the density of joints is not some artistic whim of the polygonal builders, but rather a strict requirement for monolithic behavior. ensuring that the entire structure acts as a single, unified body. One might assume that using megaliths would be a simpler solution, especially given the clear ability of these builders to transport and fit multi-ton stones with great precision, even across rugged terrain. But here we encounter a particular difficulty. Natural stone, being part of a geological formation, is rarely free from internal layering, cracks, and voids. Finding a megalithic block with minimal defects is not always possible. This is evident in the lower tier of the zigzag walls at Sacsayhuaman, where many megalithic blocks exhibit natural flaws. In the upper tiers, however, the blocks are smaller and much more homogeneous in quality. This may indicate that within a complex different components were subject to different levels of structural or material requirements. We see something similar at Ollantaytambo, where the quality of the stonework varies noticeably between the lower and upper layers of the facades. Another argument against constructing buildings entirely from megaliths lies in the fact that trapezoidal niches, a defining element of the architecture, are always built using masonry. When carved into single boulders or bedrock, niches take on a rectangular shape or display only a minimal inward tilt. This is particularly clear in the main temple at Machu Picchu. The lower row is made of megaliths, followed by masonry of significantly smaller blocks, and it is within this upper masonry that the trapezoidal niches appear. There seems to be no practical reason why another row of megaliths couldn't have been added to accommodate the niches. Yet, contrary to what might appear a simpler construction method, the builders opted to produce numerous individual blocks and fit them together with high precision. At this point, we should recall a few other features of two-layer masonry: the lack of bonding between the inner and outer faces, and the presence of soil used to fill the space between them. Within the framework of single lithology and monolithic behavior, such features suggest that the two layers may have functioned as independent systems, either physically separated by fill, or mechanically coupled yet still retaining some degree of freedom when not bonded. This gives reason to view the walls, and the complexes themselves, as functional constructs based on principles unfamiliar to modern building practice. A typical example of such structures is the closed-loop polygonal enclosure of modest height, often rectangular in plan. Sacsayhuaman, Rakshi, and Rumiwasi provide examples. At Rakshi, later phases included the addition of vertical height using different materials. But the upper course of the polygonal masonry clearly shows that no continuation was originally intended. These structures were deliberately designed to be low. From our perspective, they might resemble planters or flower beds, but it's unlikely this was their intended function. Moreover, the uneven finish of the uppermost course suggests that visual aesthetics were not a primary consideration in their design. In that context, the niches, which do not extend into the second course of masonry, may be interpreted as deliberate perforations of the first layer, purposefully made openings, aligned at a single, consistent height. They may also have affected certain physical properties of the structure as a whole, for example, acoustic resonance or frequency response. There are, however, exceptions to the principles previously outlined. One such exception concerns the interface between masonry and bedrock. In Pisac, for example, the complex is built upon a base of volcanic breccia, which appears dark in contrast with the reddish andesite blocks. This directly contradicts the single lithology principle. Here, different stone types are brought into direct contact. And not only is there no separation between the wall base and the foreign substrate, on the contrary, the interface between blocks and bedrock is crafted with exceptional care, often in 3 planes. Moreover, the contact surface area is deliberately enlarged by covering protruding bedrock masses with masonry. Several such outcrops can be seen at Pisac. This means that the contact between materials of differing lithology, and, in fact, of sharply contrasting physical properties, was an intentional design decision. It's also worth noting that when the bedrock is of the same lithology as the masonry, tight joining is not always observed. In Kenko and Machu Picchu, the rock and masonry are deliberately separated. In such cases, protruding segments of unworked bedrock effectively increase the contact area of the monolithic masonry plus rock structure. Similar relationships are observed where sections of raw bedrock protrude through terrace facings. Thus, despite superficial visual similarities, the integration of rock outcrops with masonry serves very different functional purposes. If the purpose of the polygonal complexes had been ritual, it would be logical to expect a consistent approach. Either systematic joining between rock and masonry, or consistent separation. The presence of both approaches suggests a technical, rather than symbolic or cultic, rationale. The term, technical purpose, is used here in a broader sense, referring to the transformation of natural phenomena for practical use. This does not imply narrow specializations like power plants or telecommunications systems. Such purposes may well be compatible with cultural or even ritual functions, for example, the use of sounds that arise spontaneously within rock formations. Another example of multilithology use is found at Ollantaytambo, where the rear of granite megaliths was backed with andesite blocks. Given that the work was never completed, we may conclude that this approach proved unviable. Subsequently, a completely different polygonal complex was constructed nearby, featuring what we now recognize as standard architectural elements, facings, trapezoidal niches, and large-scale geometric configurations. Can we find analogies to modern technical systems that reflect the same architectural logic seen in polygonal complexes? All complex machines use multiple materials, whether internal combustion engines, electric motors, or printed circuit boards. So the comparison should likely be made with something simpler. For example, a mechanical gearbox which can be made entirely of steel, housing, gears, bearings, and bushings. The type of metal may vary from component to component, but these differences can be ignored for the sake of the analogy. They affect durability, not operating principle. A gearbox is not a standalone device. Its purpose is to transmit mechanical power via rotation. Both the energy source and the loaded drives exist outside the gearbox. It functions as an intermediary. This analogy implies the loss of contextual completeness. We see only part of the system, the part available to us, while both the source and the recipient remain hidden. And to complete the analogy, recall that no mechanical gearbox operates without lubricants, whether oil or grease. Likewise, polygonal complexes do not exist independently of water. They form an integrated system with hydraulic features. Such a close and essential connection points to the fact that the functionality of polygonal complexes is highly sophisticated and required an integrated systemic approach. All the analogies we've discussed should not be seen as attempts to explain the actual purpose of polygonal architecture. Rather, they simply illustrate that the rationale behind building constructions with tightly fitted blocks and complex geometric forms may lie outside conventional architectural frameworks. The properties of single lithology and monolithic behavior lead to direct and non-negotiable consequences. For example, polygonal masonry cannot transition into coarse, mortar-based construction. That would contradict the principle of monolithicity and the very idea of tight-fit dry joints. This is why upper additions made from rough stone as seen at Rumikolka or Pyatkin clearly could not have been part of the original complex. When additions were necessary, they were built in a different style, using a different type of masonry and differently sized blocks. Such modifications can be identified in many complexes, a topic in its own right. But for now, it's important to note that these additions do not violate the core principles of monolithicity and single lithology. In the end, polygonal complexes should not be seen merely as architectural structures, but rather as holistic systems in which geometry, material composition, and methods of joining elements are all subordinated to the task of managing specific processes, for example, the control of water flow. The rationality of these forms is not decorative, but functional. Precise block fitting, lithological uniformity, the absence of mortar, and the overall complexity of the system. All of these are signs of intentional environmental design with specific physical properties in mind. This approach allows us to consider polygonal masonry as a form of ancient engineering, based not just on aesthetic execution, but on an understanding of the internal behavior of materials. With that, we conclude this overview of one of the key properties of polygonal architecture. Thank you for watching, and see you in the next episode.